All right. Then we talked about rotational motion. So we had already talked about torque, which is, to me, it was a little backwards because it seems like rotational motion is a precursor to statics, but that's how your book organized it, and that's how we did it. And it's fine. It worked out great. We talked about how rotational kinematic equations are the same as the linear kinematic equations, except we replace the delta x's with delta thetas. We replace the v's with omegas. We replace the forces, f's, with taus, the accelerations with alphas, the m's, the masses, with moment of inertia. A lot of people did their street physics videos on that too. And the momentum at p with L, angular momentum. It's all the same as what we did with linear, except it's describing rotary rotational motion. So as Caitlin was asking earlier, I think it was Caitlin, those are related to each other, linear and rotational. If I go around a circle faster, it requires me to move faster, tangentially. And if I go slower, I'll go slower. So it's related by how far from the middle of the circle we are. V equals R times omega. That's where that equation comes in. That's the relationship between the linear and the rotational. Torque equals, we said, force times the distance from the pivot times the sine of the angle between them. It also equals, if we use Newton's second law, F equals ma, torque equals I times alpha. That was in one of the videos, which I thought it was fun to see that. Okay, onward and upward. Questions about rotational motion? We've talked about it already a little, so I went kind of fast.
Will we be provided the moment of inertia equations for the different shapes?
Yes. Okay. I remember putting that on there. It's on the test itself. After rotation, after they did rotation, we did fluids and pressure. Did we do something in between rotation and fluids in your class?
Oh, I think so.
Yeah, I'm kind of blanking. It seems like there was time in between those two chapters, but maybe there wasn't. All right. Well, that's what's next on this sheet. And this is from, I know that they were parallels, but there was a little bit of a disconnect with the statics. With pressure, we just went over this. So like, this is going to be fresh in your mind. We talked about Pascal's principle. If I increase the pressure on part of a fluid, it increases throughout the entire fluid. We talked about Boyle's law, which was the relationship between pressure and volume in a contained system. So if I increase the volume of that system, I'm going to decrease the pressure within it because there's more space for all those fluid molecules to take up. So the pressure gets reduced. If I decrease the volume, I'm squeezing those fluid molecules together and the pressure increases. We talked about density of the fluid being mass per unit volume, which is important when we talk about Archimedes' principle, which is buoyancy. Buoyant force equals the weight of the fluid displaced by the object that is in the fluid. If you've got an object just floating on the surface of something, the buoyant force equals the gravitational force because it's not accelerating, it's not moving. It's floating above the surface because it's not displacing its own volume in water or in whatever fluid it's floating in. It's only displacing enough fluid so that it weighs, the fluid that's displaced weighs the same as the object itself. If I push that object under the water, the weight of the fluid displaced would be bigger than the weight of the object itself, and it would float to the top. If the object was more dense, then the weight of the fluid displaced would be less than the weight of the object because the fluid is less dense, the volume is the same, so the mass of the object is bigger than the mass of the fluid, and therefore the weight of the object is more than the weight of the fluid. So it would sink. It would sink to the bottom. When it gets to the bottom, that's kind of a fun question. I don't think I asked this one, but it's a fun question to answer. When it hits the bottom, it's sitting on the bottom of the container of fluid, the gravitational force is still bigger than the buoyant force, but there's also a normal force pushing up that balances the two out. So as it's sinking, the buoyant force doesn't change. The weight of the fluid displaced doesn't change. So the buoyant force doesn't change either. Give me 1 second. I'm going to make it. I just thought of, I don't know why. I have a weird train of thought sometimes. And I just remembered I have to do something for my online class. Talking to you about this made me think of it. And if I don't write it down, I'm going to forget. All right, cool. I'm back. I think that was the last thing we did. No, we did fluid dynamics too. Sorry. So we didn't just stop at fluid statics. We also did fluid dynamics. That was Bernoulli's principle. Faster moving fluids will feel less pressure, which is a little counterintuitive. And a couple of people got that wrong in their explanations in their videos, their street physics videos. They said it's creating a vacuum, but that's not what's happening. It's just that when fluids move faster, there's less pressure on them. They feel less pressure. So it's not because there's no fluid there. It's the fluid that is there is under less pressure. I think in the videos, the folks who said that understood that idea, but they didn't say it right. A few, not everybody, but a few did. And we also talked about flow rate. Flow rate is equal to the area through which a fluid is moving multiplied by the velocity of that fluid. So it's, if you do the units, area is like meters squared and velocity is meters per second. So you end up with meters cubed per second, which is volume per second, volume per unit time. And that's what we want. That's what the flow rate is. It's the volume of fluid in a given amount of time. Next semester, this is a preview for those folks taking Physics 2 next semester. That idea of area multiplied by the velocity vector it's called flux. And it's part of how we generate electricity is using magnetic flux. It's magnetic field passing through an area. In this case, it's a fluid moving through an area, but there's a special name for when we're looking at how much stuff is going through an area, and it's called flux.
So flow rate is area times volume?
Area times velocity.
Velocity. And then
which equals the volume per unit time. So don't get confused on your B's. I didn't mean to confuse you. But that's what you're getting. You're going to get meters cubed per second, which is volume per unit time.
Mm-hmm. Yeah, and that's why it's the same flow rate, even though there's less. I'm trying to think of the word.
Yeah, if you constrict the area, you get a higher velocity because the flow rate stays.
Has to stay the same. Yeah.
Yep.
And then could you explain Boyle's law? I was trying to take down everything else. And I didn't really hear you.
Boyle's law is that the product, if everything else is contained and held constant, then the pressure times volume is conserved as well. So if I increase the pressure, I have to decrease the volume to keep that number the same. PV equals PV.
I see. Yes, which is and that kind of carries over to like the big pipe, little pipe. Is that kind of because like the bigger pipes have less pressure, or they have more pressure, don't they?
Well, it's different when it's moving. So Boyle's law is a static thing.
Yes.
When it's moving, it's more complicated. It becomes fluid dynamics, but faster moving fluid feels less pressure.
Yeah. Okay.
But those are related. The flow rate and Boyle and Bernoulli principle are related to each other
because they're dynamics.
Yeah, if you constrict the flow of a fluid, it's going to move faster, and it's going to feel less pressure because it's moving faster.
Okay, thank you.
Yep. All right, cool. That's a lot of stuff. But I think that's it. I think that's all the stuff we covered. How are you feeling about it? Like, you remember all of those things?
I think I'll be okay.
Okay. Do you want to go through some questions I've got listed here?
Sure.
All right. Cool. I'll ask, you answer. If you can't answer, I'll help you. Okay. If I do a round trip, what's my displacement?
0.
Yeah, because?
They're starting and stopping at the same point.
Yep. All right, list me some vector quantities and list me some scalar quantities. Ready, go, vectors, go.
Vector would be like,
Velocity.
Yep.
you know, what
Acceleration.
displacement, like,
Yeah. Velocity, acceleration, displacement, momentum,
Omega.
omega. Yeah. Torque is also a vector.
And like the scalar would be like mass.
Yep.
moment of inertia.
Moment of inertia. Good. Yeah. Awesome. Speed is actually a scalar quantity. Distance is a scalar quantity. Good call. All right. If I give you a position time graph and I asked you to find the largest velocity, how would you do that? What would you look for?
Largest slope.
Yep, just look for the steepest slope, either positive or negative, just the biggest. So if I asked you at what point in the graph are you the farthest away from the origin, from the starting spot, how would you find that?
Go to the farthest point from, like, to the right.
Well, if it's a distance versus or a position versus time graph, the farther to the right is the farthest time, but not the farthest distance.
The
Yeah,
highest point on the y-axis.
Yeah, so we gotta look for the highest or the lowest point. So either the maximum in the positive or the negative, but the farthest from the origin will be either the highest or the lowest, the highest above or the lowest below the 0 point. Does that make sense?
Yeah, that makes sense.
All right, cool. You might have been saying it, but I want to make sure that it's clear. So we know that objects will fall at the same rate. Projectile motion wise, like it doesn't matter what they're doing in the X, they'll fall in the Y direction at the same rate.
Isn't gravity the only force acting on a projectile?
Correct. That's exactly right. So if I throw a ball horizontally, just flat, straight out, like rolling it off the edge of the table,
Yeah.
or dropping it off the edge of the table, doesn't matter. They're both gonna hit the ground at the same time.
Right.
Yep. At the top of, like, if I don't throw it flat, I throw it up in the air.
Yes.
Let's say I throw it straight up. Let's keep it simple.
Mhm.
Straight up in the air. At the very top, when it leaves my hand, it's got a positive upward velocity, but a downward negative acceleration.
Correct.
All right, gets to the top and comes back down. It's got a downward acceleration and a downward velocity. What are the acceleration and velocity at the top of the throw?
Isn't velocity 0, but acceleration still at 9.8?
It is. That's right. Good call.
And then for projectile motion, there's like a constant velocity in the X direction, right? Which is the muzzle velocity.
Yep.
Yeah.
Because there's no acceleration. As long as we're ignoring air resistance, there's
Right.
nothing to change its velocity. In reality, if you're throwing something far and fast enough, it's going to be a blunted parabola. So it'll be a little steeper falling. That's why a Hail Mary pass will come down like more vertical,
Yeah.
because it does have air resistance slowing it down in the X direction. But for any of the problems we've ignore air resistance, and it's a parabola.
I think you just cut out, at least for me.
Oh,
Yeah.
that's
same.
not good. Sorry. All I was saying, can you still see my screen?
Yeah,
Yeah.
we can see it.
So it makes this parabolic shape because in the Y direction, it goes up and comes back down, and it's just following the same as if I just threw it straight up. And in the X direction, it's just moving straight out, and there's no acceleration in the X direction because we're ignoring air resistance. If we didn't ignore air resistance and the thing was moving fast enough and far enough, there would be a deceleration, a negative acceleration in the X, and the parabola would look like this.
Mhm.
Which is why like a Hail Mary pass comes down into the, like almost vertical into the arms of the receiver. But for all of our problems, we're looking at relatively slow and relatively small duration types of things. So we ignore air resistance. We don't even worry about that. It's just fun to know stuff. So like for your future reference.
So a gas pedal, a brake pedal, and a steering wheel can cause acceleration.
That's absolutely correct. Yes.
Because a change in direction and like a deceleration or acceleration is a acceleration technically.
Yep. Perfect. If my car breaks down, I put it in neutral and I have to push it. I'm pushing on my car with a certain force, and it accelerates the car forward. Let's say I'm pushing with 500 newtons, and the car accelerates at 5 meters per second squared. I'm just making up numbers so we can like make them easy. So I push with 500 newtons to get the car moving, and it accelerates at 5 meters per second squared. How much force is the car pushing back on me with?
Would it be less than 500?
Well,
know,
what does the law tell us?
It would be
Let's
equal.
refer,
Right?
If
let's
it's
refer to the
that-
law.
If it's not moving, then it's equal and opposite.
It is moving, but
So-
even if it is moving, what
Still
does
equal.
Newton's third law say?
So it'd be 500 newtons.
Yeah. So a little bit of a trick question there, right? Like thinking about Newton's third law, the net force on the car is going to be in the positive direction. So it's going to, because it's accelerating, the net force, we could figure out the net force on the car by using F equals ma.
Right.
I'm pushing with 500 newtons. If we knew the mass of the car, we can put that in, figure out what the net force would be to give it a 5 meter per second acceleration. But the second law pair, if it's pushing on me, that doesn't affect the car. That affects me. So
Right.
I'm pushing with 500 newtons forward. It's pushing on me 500 newtons backwards. And it doesn't matter if it's accelerating or not. Whatever I'm pushing with, it's pushing back with the same, because that's the law. Newton's third law, equal and opposite.
I have a question about projectile motion again.
Okay.
So if let's say we have like a cannon, and
Okay.
it has like a muzzle velocity of like 100 meters per second.
Like in the lab.
Yeah, like in a lab. And then we have a angle at which it's shooting, and let's say it's like 30. And then so with that, we could find the x and y components using cosine and sine. And then with that, we can find the hypotenuse using the Pythagorean theorem to find how fast it goes. Is that kind of?
Well, you said we had the muzzle velocity, so we already
Yeah.
know that.
Although we can find the distance it goes.
Yep. So in order to find out how far it goes, like delta x here, if we wanted to know that, we would need to know how long it takes. Because the velocity in the x direction is, there's no acceleration. Acceleration in the x equals 0. So we don't know that. But if we found the time, then delta x is just going to equal v initial x times t. But we don't know the time. We got to find it. Well, I'm not drawing this to scale, but it's going to follow a parabolic path, right?
Mhm.
All right. It's going to take half of its time. We're using symmetry to, I knew it. The cat came back. She loves physics. We're using symmetry to our benefit. In the y direction, it's v y final. When it gets to the top, is going to equal 0, because it's going to be on its way up and coming down. It's going to take, we'll call it t over 2. That's how long it's going to take to get to the top. It's going to take as much time to get to the top as it takes to get back down to the bottom. If I can find that this time, the time it takes to get to the top, if I double it, I'll get the total time. And that's what will go in right here.
Yeah, so we use an equation that has everything except for time in one of the directions. I think like use the y one because we have VYF. And then we can use that time to find the x components.
You got it.
Nice. Let's make sure. So,
I don't know if I put a projectile motion problem that's this complicated on there, but that's definitely a fair game question. It's not that bad, honestly. It's just multiple steps. I don't know if that helps, but like, it really, some people look at it and say, what do you mean it's not that bad? That's terrible. But it's just a bunch of steps, but no one step is that hard. I believe in you and know that you're capable of doing it. That's validation. I'm validating you. Okay.
I have
Next.
a question that's unrelated.
Okay.
Are we going to need to know the universal gravitational like
Constant.
equation and stuff?
Well, the equation is on the equation sheet, and the constant I think is on there too. I mentioned that before. I don't know whether or not I put a gravity problem on there. I honestly don't remember. But do you want to go over it real quick? It's if I have mass 1 and I have mass 2, and I know how far apart they are, whatever this is, call it x. They're x distance apart, x meters. The gravitational force, Fg, is going to equal capital G times m1 times m2 divided by the distance between them squared. So capital G, you don't have to memorize it, it's given to you, but it's 6.67 times 10 to the negative 11th. And it's just a matter of plugging them in. More than likely, if I did put this in there, it's going to be a multiple choice question that says, hey, if I have a satellite or a spaceship up in orbit, and I move it so that it's 3 times as far away from the center of the Earth as it was before, what happens to the gravitational force?
Can you repeat that?
Yeah, I'm going to take R and I'm going to go 3 times as far. So I'm going to be, I've got my planet here. I've got a satellite. It looks like candy, but it's a satellite. And it's going around in its orbit. And Zelda, I know you're super excited about physics. So this was the initial R, the initial distance. But now I moved it. So now it's 3 times R. What happens to the force of gravity?
Isn't it 9 times less?
Yep, it's going to be 1/9 as big or 9 times less. That I don't know how you say that exactly, but yeah,
Right.
it's going to be reduced by a factor of 1/9
Yeah.
Question.
because R squared. What happens to the centripetal force required to hold it in orbit? Oh, that's a great question. I like that.
Force, wouldn't it increase?
Well, centripetal force, Fc, equals mv squared over
divided by
R.
R. So it gets a lot smaller.
It
Yeah.
requires a third less force,
3 times less.
Interesting.
but gravity is providing 1/9 as much force. So it gets a little bit funky.
Yeah, so it is technically harder.
That helps. Thank you.
You're welcome. Oh, who asked that? Colin asked that question? Or was it Zach who asked about gravity?
That was I think it was Caitlin.
Caitlin has-
That was
Oh.
me, yeah.
Oh my gosh, I gave them credit for your question. Oh my gosh. Sorry.
All good.
Then yeah, thank me. I answered your question. I'm awesome. All right. What time is it?
Oh yes.
I've got about 5 minutes. So
Could we quickly go over the unit conversions for like meters squared and meters cubed
sure.
for like fluids?
Can we also finish like the conceptual problems that you said you had for us to go over that we started doing?
Sure. We are most of the way through them because a lot of the
Okay.
questions you just asked hit on the stuff that I was going to ask you anyway. So those were great
Perfect.
questions. So 1 meter is equal to 100 centimeters. 1 square meter is going to be 1 meter on one side and 1 meter on the other side, which means it's 100 centimeters on one side and 100 centimeters on the other side. So instead of 1 times 1, it's 100 times 100, which is 100 times 100, 10,000 square centimeters. So 1 meter squared is equal to 10,000 centimeters squared. All right, cool. A cube that is 1 meter by
It's
1
the
meter
same thing except
by 1
with
meter
3.
is 1 cubic meter. But that's 100 centimeters by 100 centimeters by 100 centimeters, which is 1,000,000. I'm putting my pinky by my mouth. Cubic centimeters. So 1 meter cubed is equal to 1,000,000 centimeters cubed.
So to find centimeters squared from meters squared, we multiply by 10,000. To find,
Well, it's the same unit conversions you normally do. So if I
Yeah.
have 5 meters squared, how many square centimeters is that? Well, I got to get rid of the meters squared on the bottom and multiply by 10,000 centimeters squared on the top. The meters squared cancel out.
okay. I don't know why that just like domes me for some reason. So weird.
It's tricky because you train yourself to think centi is 100 because it is, but centimeters squared is different than centimeters. It's a different thing you're measuring.
Yeah.
The follow through, like I'm swinging a baseball bat, the follow through increases the time it's in contact, which increases the change in momentum. It's the same amount of force applied for a longer time. Delta P equals F times T. If F is the same and T is increased, then delta P is increased too, which means the ball is going to leave at a higher velocity if I hit it with a bat. A roller coaster, where's the potential energy the highest?
At the
Up.
top, no,
And where's the kinetic energy the highest?
the bottom of the hill.
You got it. Conservation of angular momentum. If I am spinning around, I pull my arms in. A bunch of people did this video too, which was fun. I'm spinning around, I pull my arms in, my I value goes down. Since L equals I omega and L is conserved, that means L is the same before and after. If I goes down, omega has to go up. If
Yes.
I goes up, omega has to go down.
Cool.
If I'm pushing on a door and I'm pushing on the door at some angle to the door, I'm going to get less torque.
Mhm.
This happens sometimes when I'm like carrying too many bags. I'm trying to shut the door and I push and my hand kind of slides off of it and the door doesn't quite shut. If I just push straight on, it would shut because F times the
FR.
distance from the pivot, force times the distance from the pivot times the sine of the angle. The smaller the angle, the smaller the torque. Changing angular momentum. So changing regular momentum, linear momentum requires a force. What does it take to change angular momentum?
Angular.
Angular force. What's another word for angular force?
Centripetal force.
No.
Rotational?
No. Starts with a T.
Torque.
Yeah, torque. You got it. Torque. A torque causes changes to rotation. A force causes changes to motion. So if I want to change the angular momentum, it requires a torque to do that.
Okay. Yeah.
All right, cool.
What about isn't it like, I remember centripetal or rotational velocity and rotational acceleration, they're kind of like different or something. Like
Say it one more time.
rotational acceleration versus rotational velocity.
Well, they're as different as,
They're not the same as centripetal acceleration and velocity because they aren't going the same speed, right?
all right, we have 3 different types of acceleration. So we have like delta X, V, and A. We have A sub C, and we have alpha. All right, we're looking at it from above. This is a merry-go-round. We have Zach sitting there. We have Caitlin sitting here, and it's spinning around like this. And then I am out here on the edge because I'm a fun physics professor, and I'm applying a force. Apply a force to it, which is at a distance from the pivot. So I'm applying a torque to it. All right, cool. So I apply a force, I apply a torque. Both Caitlin and who did I say? Did I say Zach?
Yeah.
And Zach are both going to accelerate. Now, linearly, to make the circle, Caitlin is making a small circle and Zach is making a big circle. So the displacement is going to be bigger for Zach and the velocity is going to be bigger for Zach. And that means that the acceleration is going to be bigger than Zach, or for Zach. So Caitlin is going to go around a small circle in a given amount of time, which means she's going to start at 0 velocity, but be speeding up. But she's not going to speed up that much because she's never going to go that fast. Zach is going to get faster and faster and faster as he's going around. They're both going to get faster and faster and faster, but Zach's going to increase faster because he's going to go from around a bigger circle in the same amount of time. So A sub C is going to equal V squared over R. Zach has a bigger R, but he has a bigger V as well, and it's V squared. So he's going to have a larger centripetal force. He's going to get pulled to the outside more. It's going to require more force, and he's more likely to get flung off the edge of the ride. Because yes, R is bigger, but it's V squared, and his V is bigger too. All right. Alpha is going to be, so we have theta, omega, and alpha. Their omega is going to be the same. Their theta is going to be the same. So their alpha is going to be the same as well.
The omega is the same.
Yeah. If Zach, you go around the circle once, how many times is Caitlin going to have gone around the circle?
Once.
Yep. If you go around the circle twice, how many times is she going to go around the circle?
Twice. Yeah.
Yep. And it's happening at the exact same amount of time. So if omega is theta per unit, and then if that's the same, and omega is delta, sorry, if alpha is delta omega per unit time, then your theta, omega, and alpha are all going to be the same.
Yeah, I thought that, centripetal was a little bit different than rotational. So
It is. They're related to each other.
Yeah.
Going around in a circle requires force.
So centripetal acceleration and velocity is different, and then rotational alpha, omega, and theta are the same because it's in terms of
Well, they're not
degrees.
the same. They're in the same train of thought, the same method of description, the same content heading. They're not the same thing. Theta is one thing, omega is something different, but they're related to each other.
Oh yeah,
These
I know. Yeah,
are
but I
related.
mean, like they're going to be the same between me and
Oh yeah. Oh right. Sorry, I misunderstood you. Dang it! I was doing so good. I had to go say something stupid.
That's no worries. Thank you. That cleared it up for me.
Good. All right, folks. That's about all the time I've got. I'm going to stop sharing my screen so you can see all this. She jumped in for this.
And so I wasn't here for like the recording talk. So
Yeah.
I see that we are recording, but I don't think you are. How's it gonna like work? Where's it gonna be posted to?
Lindsay, do you want to load it, like make a YouTube video, make it unlisted and share it? You could send it to me.
Yeah,
And
or I can send it to you. I think I'll see if it just lets me send the file, because I think it'll be an MP4 and I might be able to just send that to you and then you can send it to those who email you.
I could do that. I can even post